Today we will see the next example that is example number 8. In this example we are given a simple formula in which we have to apply Ampere circuital law. Now as per as given information, we are given one figure. The actual figure that is given in the textbook is somehow drawn as this figure that you are finding right now. In this, what we are given that actually this is the actual picture of that figure. Here I have shown the vertical picture of the question. They have shown all these things in a horizontal form. So first of all, we will understand that what is given in our question, and for that we will read the information of the question on page number 149, example number 4.8. It is given that figure 4.15 shows a long straight wire of a circular cross section of radius A carrying steady current I. The current I is uniformly distributed across this cross section. So calculate the magnetic field in the region where R is less than A and R is greater than A, where R is the region taken inside and outside the wire. So here now I will explain that what is given as per as the question of the text. See, here in this question we are actually provided two small information, and that is what? First of all, we are given this wire. So you can see this wire right now. In this wire we consider that it is of infinite length. So the length of the wire is considered as a very long, straight, say infinite. Here again I would repeat that infinite means the length of the wire is very big in comparison with the radius of the cross section of the wire. So here radius A is the radius of the circular cross section of the wire, and I is the total current passing through it. But as it is given in the question that the current I is uniformly distributed across this cross section, so this cross section we can say that it is given by pi a square. Here I can explain that this is the pi a square, that is a cross section of the wire. Through that the I current is passing through it. It is given that as shown in the figure that 1, 2, 3, 4, 5 are those cross section part, and these are the uniformly distributed current. So these 5 lines combines and makes the total current I. So here in the upper part of the figure I have explained that also. Here we can see that here in this region we can see and we can explain that the total current I is a combination of 1, 2, 3, 4 and 5. So all these are uniform and equal current which are distributed equally into that whole cross section that is given over here. So in whole this cross section, all the current are distributed uniformly. Now we are asked to find out condition 1, in which we have to show that we have to find out the current in the place which is outside. See here it is outside the current. It is given with radius R2 which is greater than A, and in other part as shown in the figure with a blue circle that is indicating the inner part. So here in inner part not all the current is covered, only few lines of the uniform current is covered. So here that is the another part that is given with the radius R1 in this question. Now what we will do, we will find the magnetic field by applying Amperian circuital law. So now how to apply the Amperian circuital law? For that we will move towards the figure 2. In this figure, it is the another view of the same question it is given here. Here in this question we can see that current is coming from bottom to top. So current is going in upward direction. If we view from this point C, here I am going to write the point as a name, see, this is the cross section that I am showing. If we view from here, what we will find is shown in the next figure. So the next figure is the same view. When we view it from the upper part, what we find is that all the 5 lines of the current are indicated by dotted line. That indicates that all the currents are coming out from that cross section. Here that big green loop is nothing but this green loop as shown in this figure above, and this blue loop of radius r1 is also nothing but the blue loop as shown in this figure. And obviously the cross section of the wire has a radius a and its area is pi a square. So this is the cross section view that is of the given wire. Now we have to find out the magnetic field. We are taking two cases. One case is outside the wire and second case that is inside the wire, and we will apply Amperian circuital law. So how we will apply Amperian circuital law? First we will see for the region that is R2 greater than A. So here for the green loop we will first focus over here. As per as Amperian circuital law, we know that our main equation is, that is simple one, but it is clear that integration B dot dl on a closed loop is equals to mu 0 into I which is enclosed by the loop. So we will apply this equation and find the magnetic field. Here it is very clear that in the previous section also we have learned this, that Amperian loop, it is labeled 2 over here and is a circle concentric with the cross section. So it is very clear with this cross section, it is concentric. So the center of that Amperian loop and the original wire has the same, and that is concentric part. Now left hand side, as per as Amperian circuital law, that is B dot dl, I have written here B dot dl and that is B dot dl. Now here the direction of magnetic field and the current that is in the same direction as shown over here, that direction and the length of the Amperian loop, they both are radial in nature, and that is that part with an anti-clockwise direction. When we show the current and we show the current that is coming outside from the wire, then the magnetic field will be in the anti-clockwise direction as we curl the finger around that. So here the magnetic field will be in anti-clockwise direction in such a way that it also coincide with the small dl distance, and therefore they both are in the same direction in the tangential way. Now here the radius is r2, so we can say that it is equals to b into 2 pi r2. Now here for the right hand side, that is mu 0 IE is an enclosed current by the Amperian circuital law. So here it is obvious that total current is given I, that is a combination of 1 2 3 4 5, and all that currents are covered by this green loop. So the total current is I obviously here. So here in RHS it is given that enclosed current by amperian loop, and that is I. So when we put these two values, one, that is B into 2 pi R2 is equals to mu 0 into I, where I is enclosed current by the amperian loop, and then it will be the answer like B is equals to mu 0 I 2 pi R2, that is mu 0 I upon 2 pi R2. This indicates that for the outer region, the magnetic field is inversely proportional to the distance from the wire, and as we move further away from the wire, magnetic field will also decrease because it is having a relation B proportional to 1 upon R. So this is the case when magnetic field is outside the wire, that is given by the green amperian loop. Now case number 2. In this case number 2, we want to find the magnetic field inside the wire. Now inside the wire, actually as it is given that the total current is distributed uniformly, but we are taking blue loop as shown here, and obviously when we are taking this blue loop, current 1 and 5 as shown in this figure are not enclosed by this amperian loop. So we want to find that how much amperian loop or how much current is enclosed by this amperian loop, and therefore what we will do, we will find out a simple method that if the total cross section area is pi a square, as I have shown over here, that if total cross section area is pi a square, then current enclosed is I. But here obviously for the loop we are taking current as we go through the figure, it is enclosed by the blue loop. Blue loop has a radius r1, so it has cross section also pi r1 square. So we have written that if the cross section area is pi r1 square, then what will be the current enclosed by it? And therefore by applying this chocolate equation means that is cross product here, so cross multiplication when we apply, we find out that IE is equals to I into pi r1 square upon pi a square. When we simplify it, we find out that I is to be I into bracket r1 square upon a square, where r1 is a radius of amperian loop, where a is a radius of a wire or the cross section of the wire. Now by applying this equation, when we apply it in amperian circuital law, we find that left hand side of the equation, that is B dot dl, will have behavior that is B into 2 pi r1 as I have shown in the previous case also. And if we move further, we apply RHS as a mu 0 into IE, where IE is enclosed current that we have found over here in equation 2. When we apply this equation 2 at this place, then it will be mu 0 I r1 square over a square as RHS, and then we combine equation 3 and 4 and we get the result as B into 2 pi r1 is equals to mu 0 into I r1 square over a square. When we make B as a subject, when B becomes subject, then all the terms will go to the denominator of the next part, and that is mu 0 I upon 2 pi r1 into bracket r1 square over a square. Now we simplify this. When we simplify this, we get that B is equals to mu 0 I upon 2 pi into r1 upon a square. Now here mu 0, I, 2 pi and a square all are constant, and therefore we can say that magnetic field inside is directly proportional to the r, as it is shown in the equation number 2. So equation number 2 indicates that magnetic field inside the cross section wire is directly proportional to the radius of that Amperian loop we considered. So if we draw the graph related to this, we can simply show it by this figure. Here the first blue dot indicates that it is the region inside the radius a. So r, when taken inside wire, it follows directly proportional to the length. So magnetic field is directly proportional to the radius of the region, and if we take radius or the Amperian loop outside the wire, it will decrease, like as shown in the figure as a green dots. So here for blue dots we can say that B is, which is inside, is directly proportional to R, while for the for the green dots we can say that B, which is outside, which is inversely proportional to the radius or the distance. And here this A is actually exit on the surface of the wire, and which is the maximum current I follows through it. So this is I maximum. Obviously B is also maximum at this point. We can say that if we intersect this line, we get this is to be B maximum. So this is I maximum to be I. At that time B also becomes B maximum. So this is the information of example number 8. In this example, that is example number 4.9, we are given that a solenoid of length 0.5 meter has radius of 1 centimeter and is made up of 500 tons. It carries a current of 5 ampere. So what is the magnitude of the magnetic field inside the solenoid? Now if we consider over here that this blue color line or blue color loop is said solenoid of length 0.5 meter, through which the current is supposed flowing in anti-clockwise direction, such that at the point upper part of this loop it is directed outside, suppose, and at this portion, that is below part loop, the current is going inside. So if this is the direction of current, we can say that the magnetic field will be on the axial line, that is moving from left to right, which is indicated by black arrow in middle of the solenoid. Now we are also given that the amount of current is 5 ampere. So the amount of current is also given, that is 5 ampere, and we have to find out the magnetic field inside this solenoid. Now obviously we have, that is equation of B for solenoid is equals to mu 0 into small n into total current I. Here we know that small n is the total number per unit length, that number of turns per unit length. So we can say that this is number of turns per unit length. And here what is this value? So here it is very clear, we are given total number of turns as a capital N, and the length of the wire is given to be 0.5. So Here we apply the equation, that is 500 over 0.5, that is 1000 tons per meter. Now using this value in above equation, that is mu 0 ni, this equation number 1, we can get the required result. So when we apply it in this above equation, what we will get, that magnetic field B is equals to mu 0 into 1000 into I. Now we are also having the values of mu 0 and I. We will put that mu 0 as a value 4 pi into 10 raised to minus 7. Small n is observed, that is 10 to the power 3, and I is a current, that is 5 ampere. It is given in this question. So ultimately the resultant answer is 6.28 into 10 raised to minus 3 Tesla. So this will be the magnetic field over here inside the solenoid. Here again we have considered that this solenoid is a long solenoid. See how? Why we consider it as a long solenoid? Because length of solenoid, that is 0.5 meter, is a very lengthy with respect to its radius, that is small a, and this small a is a very tiny value with the value, and therefore we can consider is this a becomes, or the radius will be about 1 centimeter. So we can say that, say r is 1 centimeter, then this ratio turns to be L over R is turns to be about 50. That means length is about 50 times the radius, and therefore we consider it as a long solenoid. So this is the part of the question 4.9 and the solution of it. What we had done, again I would like to repeat in a fast manner. We are given that a solenoid of length 0.5 meter. Here current is flowing, that is 5 ampere. The solenoid has a 500 tons in it, and the radius of the solenoid is given as 1 centimeter. Now we have to find out the magnetic field. We use the equation B equals to mu 0 Ni, where N is a number of tons per unit length. Here number of tons per unit length, tons be to a 1000 tons per meter, and therefore B is equals to mu 0 1000 into I. The value of mu 0 is equals to 4 pi into 10 raised to minus 7. 1000 can be written as 10 to the power 3, and I is given as a 5. So it will be 6.28 into 10 raised to minus 3 Tesla. Now here this equation is only applicable to a long solenoid. So here this solenoid is considered as a long solenoid because the length of solenoid is given as a 0.5 meter, while the radius is given as a 1 centimeter. So when we take the ratio, it turns out to be a 50, and therefore we can say that length is about 50 times more than the radius of the wire or cross section, and therefore we say it is long solenoid. So this is the explanation of the question.